This clip's about kinetics. Kinetics is all about how quickly reactions take place, and the major thing about reactions taking place is if the particles have enough energy to react, i.e. enough energy greater than activation energy, that leads to a successful collision, and then that means that a reaction will take place. Another important factor with particles colliding is they need to have correct orientation. If we think about the alkene and hydrogen bromide reaction, the alkene double bond needs to be next to the hydrogen atom because the delta plus is attracted to the double bond. However, if the HBr are approached in a different way with the Br next to the double bond, then a reaction is not going to happen. So that's the second factor for a successful collision: the correct orientation of the molecules. So this is correct orientation, this is incorrect orientation. So kinetics is all about how quickly reactions take place, and with a chemical reaction we can monitor the rates in different ways. And one way we can monitor the reaction between marble chips and hydrochloric acid or any other acid is to use a gas syringe, and a gas syringe could measure the CO2 production. As the CO2 is formed, it collects in the syringe, and the syringe moves out, and you could make markings on the syringe and to monitor how quickly the reaction is taking place. And what you can do with that is to work out the volume of gas produced per second, and that's what rates is all about. It's about either the cubic centimeters per second, or if we're monitoring concentration of a chemical, it's the change in concentration per time. And so rates is all about this. It's about the change in concentration of a reactant or product over the change in time, and it's always 1 over time. Now, just to repeat a very important idea, that the activation energy is the minimum energy required for a successful collision to occur. So that's a little bit about the practical side of things. Let's have a think about something called the Maxwell-Boltzmann distribution. Now, the Maxwell-Boltzmann distribution just shows the energy of molecules in a chemical reaction. Now, most particles do not have energy greater than activation energy at any one point. And so what this graph shows is the number of particles on the y-axis and the energy on the x-axis. And so we can see that most particles at any one time, what it shows is most particles at any one time do not have energy greater than activation energy. That's everything to the left of this line I'm drawing with the pen now. And EA represents activation energy. So we can see also on this Maxwell-Boltzmann curve the number of particles with the modal energy, that's the most popular energy, and then the mean energy as well, which is the average energy, which is always slightly right to the modal energy value. Now, in a chemical reaction, no particles have zero energy, hence it touches 0, 0 here. And notice how it doesn't touch the y-axis at this point. It suggests that some particles, very few particles, have very, very high energy, hence not touching the y-axis. So when we think about Maxwell-Boltzmann distribution perhaps as another temperature, so if this is the original temperature here, room temperature, let's say, is this part of the curve. So at a higher temperature, the curve shifts over to the right a little bit. What does that mean? It means, first of all, that the mean energy is higher. It shows that the average energy, mean energy, is higher, and the number of particles exceeding activation energy is also going to be greater. Now, the area underneath the curve shows the total number of particles in a system. So if it says the number of particles on the x-axis, number of particles with the modal energy is that many there. There is no unit, no scale, but if you think about all the lines on here, I think these lots of bar graphs added up together, the total number of particles is the total area underneath the curve. So when the temperature of the system increases, the total energy of the total number of particles underneath the curve is staying the same. So the area underneath this curve is the same as the area underneath that curve. So just think about it. When you increase the temperature, that leads to a faster chemical reaction. So more particles have energy greater than activation energy. So we can see that on the Maxwell distribution curve. So the Maxwell-Boltzmann distribution curve just shows the number of particles with specific energies in a chemical reaction, but there are no values. Back to Maxwell-Boltzmann again, this time when the temperature is a little cooler. So this is the original temperature there, at room temperature. So if the system cools down, then the number of particles exceeding activation energy will be fewer. You can see the area underneath the curve for the energy greater than A is decreased. The modal energy is actually a higher number, but the energy is lower. The mean energy is also a lower energy, as you'd expect, because if you decrease the energy of the system, you decrease the temperature, particles have less energy, they're therefore less likely to exceed activation energy. Remember, the area underneath the curve is the same because the number of particles is the same. So roughly speaking, remember you're only going to draw these out with a sketch curve, but they should look as though they have roughly the same area. Just a couple of other things to consider in rates, in kinetics. First of all, that when you're thinking about the effect on the rate of reaction, effect of temperature on the rate of reaction, go back to Maxwell-Boltzmann, apply that principle. So when there's higher temperatures, more particles have energy greater than activation energy, therefore they're more successful collisions per unit time, and it's important that that type of phrase is mentioned. It's always per unit time, 1 over T, 1 over T, 1 over T, so it's how many particles are produced per second. So at lower temperatures, there are fewer particles that have energy greater than activation energy, and so fewer successful collisions per unit time. With the concentration changes, when you have more particles in a system, there are more likely to be collisions, successful collisions, because there are more particles. So more particles in a unit volume, or a specific volume, therefore more successful collisions again per unit time. With the lower concentration, fewer number of particles, fewer collisions, therefore are less likely to be successful. And the last point is about catalysts. Now catalysts, what they do is they speed up chemical rates without actually being used up. How do they do that? They do that by providing an alternative route for the reaction to take place, which has a lower activation energy than without a catalyst. So this is an enthalpy diagram, and this is the original enthalpy diagram where we have the activation energy, and we have the activation energy with the catalyst, and you can see that the energy value is lower. Therefore, more particles are likely to exceed the activation energy in a unit time when a catalyst is present, because the energy is lower, and so the reaction takes place more quickly. Just to make a link with that and Maxwell-Boltzmann distribution, on the curve, if I use this curve here, the position of the Maxwell-Boltzmann with the E-cat would actually be a lower value around here. We're lowering the activation energy, and therefore you can see that with this new curve, this new position of the E-cat, more particles would be exceeding the activation energy when the energy for the activation energy is lower with the catalyst.